So the thing I want to kind of say to everyone about U-substitution is and Dr. Berkshire said this in class, I think it's very right. It's going to take some guessing and checking sometimes. Right? Sometimes you're going to pick the wrong thing for you, and that's okay. But the kind of driving force behind how we decide to pick or guess what we think U should be when we're trying to do U-substitution is we want to try to pick a U so that the derivative of U is already in the interval. Like that, like I think the second to last problem she was doing where it was, I think it was cosine of x over 1 plus sine squared. And we finally figured out we had to pick U equal to sine because the derivative of sine is equal to cosine. That's how we did it. Or maybe it was the other way around, but the idea is that you're always trying to pick U so that the derivative of U is in your interval. Two things about this. Thing one, it doesn't matter if we're off by a constant, which we'll see today a lot. And thing two, it's a weird way of doing two. Thing two, I should be a little more specific. When I say I want the derivative of U to be in the integral, I mean that I want the derivative of U times dx. So let's look at this example real quick. I've got the interval of cosine of x times e to the sine of x dx. There are two seemingly perfectly decent choices for U. We could pick, or we could try to pick, U equal to cosine of x. But if U is equal to cosine of x, du dx is equal to negative sine x. And you might say, well, James, we have a sine x, so that's a good choice. And I would say, well, not exactly. Because if we isolate du, we get du equals to negative sine of x dx. And here's the problem. We don't actually have sine of x dx in our interval. Or I should say, we don't have sine of x times dx. The sine of x here is inside the exponent, right? It's e to the sine of x. It's that sine of x is not really multiplied by dx. So what you're really looking for is the derivative of your choice for U to show up something as being multiplied by dx. Meaning it basically can't be stuck somewhere else. It can't be in an exponent or in a square root or whatever. So in this particular problem, sine of x is the correct choice for U. We let U equal sine of x, then our derivative, du dx, is equal to cosine of x. And then we can isolate du and say du is equal to cosine of x times dx. And look, we have cosine of x times dx, because cosine isn't stuck like by talking, cosine isn't stuck up inside the exponent. So for this one, the way we would rewrite this is, and here's another thing, I always want to make sure I focus on rewriting the dx part as a du thing first. So it's vital that we make sure that we change cosine x times dx into du. So this is going to equal the integral of, so cosine x times dx becomes du, and e to the sine x becomes e to the u. And now we're able to anti-differentiate this. This is the best one ever. The integral of e to the u is just e to the u. Good times. So it's e to the u plus c. And then for indefinite integrals, right, we'll just find the antiderivative. For indefinite integrals, we have to end with the same variable we started with. Right? If your integral is an integral of a function of x, then your antiderivative should end up being a function of x. So we have to replace our u with what u was equal to, which was a sine of x. This is e to the sine of x plus c. And that is our answer. That's our antiderivative of cosine of x times e to the sine of x dx. There's something else I want to say here. Oh, so we'll see today, in contrast, right, when you have a definite integral, although you can switch back to your original variable, usually it's better just to leave it in terms of your new variable and change your limits of integration. So we'll do some examples of that for sure. But let's just get into doing all the examples. Yeah, so Oh, sorry. This was the derivative inverse tangent. If you really want to see it, which I already started erasing. Sorry. Let's do it. So, if you want to see it, right? You start off with y equals the inverse tangent of x, and then you rewrite it as tangent of y equal to x, and then you differentiate implicitly. You get secant squared of y times y prime equal to 1. You solve for y prime, you get 1 over secant squared, and then you use the fact that tangent of y is equal to x over 1. You draw this triangle where tangent is opposite and we're adjacent, and then you find the third side using the Pythagorean theorem. It's the square root of 1 plus x squared, and then secant of y is hypotenuse over adjacent, so secant of y is the square root of 1 plus x squared, so secant squared is the square root of 1 plus x squared. So that's how you get the derivative inverse tangent is 1 over 1 plus x squared, which really we only, well, not we don't only care about, but currently we really care about that, because then if we know the derivative inverse tangent is 1 over 1 plus x squared, we know the antiderivative of 1 over 1 plus x squared is inverse tangent. So that's why we care. So let's look at a whole lot of examples. Let's look at this first one here. Let's look at the integral of x squared times the square root of x cubed plus 5. So how do I choose u? There are actually kind of, in addition to wanting to pick a thing whose derivative is also there, the other kind of guiding principle behind how you choose u is you often choose a u that is stuck somewhere. When I'm looking at this, I see that the x cubed plus 5 is inside another function. It's stuck in the square root, and we can't really get it out. That is often a good way to think, I should probably try choosing that. So if I'm going to let u equal x cubed plus 5. And then I notice that the derivative of x cubed plus 5, I have that kind of in my integral, right? My du dx is 3x squared. I have x squared. Being off by a constant multiple isn't a problem, right? I think you guys saw in class that we can divide both sides of this equation by 3 to get just what we want. So I see that I have an x squared dx. I'm going to try and make this look like I have an x squared dx. So I'm going to bring the dx over. So du equals 3x squared dx. And then multiply both sides by 1/3, or divide by 3, however you want to say it, it's the same thing. So that 1/3 du is equal to x squared dx. Great. X squared dx is going to get replaced with 1/3 du. And I want to emphasize every time, it's really, really important to make sure we deal with that aspect of changing things to u before we deal with the other parts. It might not be immediately clear why yet, but trust me, there'll be a couple of examples where you'll be like, oh, I see kind of now. So I'm going to write this as the integral of, so that's du. Oh, sorry, not du, it's 1/3 du. So you can put the 1/3 there. And then this is going to be the square root of u. And the 1/3 that's multiplying the du, or whatever is multiplying the du, we almost always, without fail, put that out in front of the integral. So if you have the integral of a constant times some other stuff, we almost always rewrite it as the constant times the integral of the square root of u, which we're going to rewrite as u to the 1/2. Right? You almost always want to write roots as powers, so you can more easily anti-differentiate them. And then du is going to be u. And now we anti-differentiate using the anti-power rule. We're going to get 1/3 times the antiderivative. So here's what's going to happen. We're going to add 1 to the power. We're going to get u to the 3/2. And then we're going to divide by the new power. But since we're dividing by a fraction, we're going to be flipping and multiplying. So instead of writing divided by 2/3, divided by 3/2, we're going to multiply by 2/3. You could also show the work, right? You could say divided by 3/2 and then multiply. But we do this so many times that it kind of gets to be natural. It's like, oh yeah, we get u to a thing and then times the reciprocal of that thing. And then plus a c. We're going to simplify just a tiny bit. 1/3 times 2/3 is 2/9. And u we have to then replace back with what u was equal to, which is x cubed plus 5. That's going to be 2/9 times x cubed plus 5 to the 3/2 plus c. Sorry, that is a 5. My 5's never looked good. It just looks worse now. So definitely jump in if you have questions, but I'm just going to keep showing you examples.
Yeah, I have a question.
Yeah, go ahead.
So like, I feel like you've already said it, but I get confused on these because I understand like the part you changed for like the u part was the square root of x3 plus 5, but I always get confused about like the x squared part. Like, what's going on with that?
Well, so here's what we're saying. We are set, and so let me actually, so here's what might help. So down here, right, so we said that the derivative of u, right, so we're saying u is a function of x. So we're saying du dx, the derivative of u with respect to x, is equal to the derivative of this, which is 3x squared. And then we manipulated this a little bit so that we could say that du is equal to 3x squared times dx, and then x squared times dx is equal to 1/3 du. Now, what might help you see this a little more easily is to actually put the things next to each other that are supposed to be next to each other. So if we wanted to, we could totally rewrite this as the square root of x cubed plus 5 times x squared times dx. And then it might be easier to see that, oh, look, x squared dx, well, that's just x squared dx, and x squared dx is equal to 1/3 du. So we're really just replacing this with something it's equal to. In a similar way, we're really just replacing this with something we've said that it's equal to. So we end up with the square root of u times 1/3 du. Does that help clarify things a little bit?
Yeah, it helps me see more like how it just like it adds to how we're just like transforming it to look different.
Something to keep in mind is that if you're doing a u substitution, you have to change every x to something with u. You can't have something with x's and u's in it. That's really kind of very, very important. Specifically, dx has to change into du, and then all the x's have to become u's. There are other ways of doing this. Some people like to say, I feel like there is another way of doing it, but I feel like it's not as good. 2, it's not the way Karana is teaching it. So I really kind of feel like, although there are other ways, the way we're doing it is the best way. Well, let's do more examples. And again, if you have questions, please let me know. Yeah. So let's do this one. Yeah, this is a good example. So let's do the integral of e to the square root of x over the square root of x. Oh, I skipped. That's all right. I'll come back to that one. Oh, it's kind of funky actually. Sure. So for this one, I'm gonna let u equal the square root of x. Not because I exactly know the derivative is showing up, right? I'm trying to think of something where the derivative is showing up, but I don't really have any other choices, right? And furthermore, the square root of x is what I call stuck, right? It's stuck in the x, and it's also stuck in the denominator. So it's definitely a reasonable choice. So if we let u equal the square root of x, we're going to find the derivative. So which, right, this is x to the 1/2. So my du dx is equal to 1/2 x to the negative 1/2. Now, I really think it's going to be in our interest to rewrite this. I'm going to write it as du equal to 1/2. And then x to the negative 1/2 is 1 over x to the positive 1/2 dx. Finally, I'm going to bring the 2 over here. So the 2 du equals, I'm going to write 1 over, instead of x, I'm going to write 1 over the square root of x dx. And now it might be easier for you to see, oh yeah, look, I have a 1 over the square root of x times dx. So this is a good choice because we can replace this with a du or a 2du. Okay, here's what I want to say. So don't write this next part down if you're writing this down. If we kind of do this not very carefully, we're going to end up in a bad spot. Let's say I see, oh, look, there's a square root of x. Square root of x is equal to u. So I'm just going to make all my square root of x's u's. So I get e to the u over u. But then I've got dx. That's a problem, right? I've got u's and x's. The issue here is that I didn't follow my own advice. I didn't deal with making sure that dx turns into du first. That always has to happen first. So it might be a little easier to see this happen if we break up e to the square root of x over the square root of x as e to the square root of x times 1 over the square root of x dx. Now I think it's easier for people to see that all of this here is du. Sorry, actually 2 times du. And then we can deal with what's left over. So this is all spoken for, right? We don't get to say anything else about that. All of that goes into equaling 2 times du. E to the square root of x, well, the square root of x is u. So this is going to become e to the u. And then we can write our integral as the 2 du, the 2 constant multiple can just sit out in front of the integral. So anything that's multiplied by du, just throw it in front of the integral. It's always going to come out to the front. This can be 2 times the integral of e to the u du. Everything has u's in it. We're in a good place. We know how to anti-differentiate e to the u. It's just the u. So we get 2e to the u plus c. And then we have to replace u with what it's equal to. So we end up with 2e to the square root of x plus c. And if we wanted to, we don't have to, but if we wanted to, we could check that this is correct by taking the derivative of this. So if you took the derivative using the chain rule, there's like 5 things at once in it. The derivative of 2 times e to the square root of x, I'm going to leave off the plus c because we know the derivative of c is 0, is going to be 2 times the derivative of e to the stuff is e to the stuff times the derivative of that stuff. But the derivative of the square root of x is 1 over 2 times the square root of x. Right? It's 1/2 x to the negative 1/2. So this is equal to 2e to the square root of x times 1 over 2 times the square root of x. But the 2's cancel, and we exactly get e to the square root of x over the square root of x, which is what we should get, right? If we say that the antiderivative of this, then the derivative should be the function's derivative. Okay. Question?
I have a question. So, how did you get the e to the u?
Right here?
Yeah.
So so I did erase, so I erased the substitution. Let me go right back in. So the choice we made, and this is really like this came from us. We're like, oh well, I think it might make sense to let u equal the square root of x. So then when we rewrote this as e to the square root of x times 1 over x, e to the square root of x, really we're just replacing this square root of x with u. So that e to the square root of x is equal to e to the u.
Okay, I see.
Good.
Thank you.
You're welcome. Here's the side. So let's see. Is that one? Sure. Let's try this one. I might have you guys do some of this one. Let's try the integral x plus 3 over x squared plus 6x plus 1 squared dx. Let's make it, instead of square, let's make it to the 20th power. It's a little more interesting. So what might be a good choice for you?
Denominator.
Right. So let
Inside.
me say that one more time, sorry.
The inside of the denominator.
Yeah, exactly. Right. So one thing to think about is you want to pick u that isn't like super crazy complicated, which is why Emily is saying we don't want the entire denominator, we want just the insides there. And there's, again, really a couple good reasons for that. One reason, the reason I like to say is because that stuff is stuck, right? It's stuck, well, it's stuck in the denominator, it's also stuck in this being raised to the 20th power. And you can't kind of get it out of there without actually multiplying it out, which is terrible. The other reason it's a good choice is because if you take the derivative of it, du dx is 2x plus 6. And I don't exactly have that, but I have a multiple of that, right? I can factor out a 2 here and say that du is equal to 2 times x plus 3, and I can bring the dx over. And look, we have an x plus 3 times dx. So I want you all on your own to rewrite what this integral is going to be equal to in terms of u. So what's going to replace the x plus 3 dx, and what's going to replace the x squared plus 6x plus 1 to the 20th? I'll give you a minute.
You're going to have half du.
I'm sorry, you broke up there a little, Chang. What'd you say?
Half du.
Yes, that's correct. Oh yeah, you're right, because I do need to divide by 2 here. So 1/2 du is going to be x plus 3 dx. So you're totally right. The x plus 3 times dx is going to be replaced by 1/2 du. And in the denominator, well, that's the easier part maybe. X squared plus 6x plus 1 is going to get replaced by just u. So we have u to the 20th power. A couple ways we can make this a little easier is we can bring the 1/2 out in front of the integral. And then instead of writing du over u to the 20, we can write u to the negative 20th power times du. So that's going to end up equaling 1/2 times, if we anti-differentiate that, we're going to get u to the negative 19th divided by negative 19 plus c. And then I would probably leave it like that. So I would probably write this as u, replace u with x squared plus 6x plus 1. That's going to be x squared plus 6x plus 1 to the negative 19th power. Divided by 2 times negative 19 is negative 38. Usually we don't divide by negatives though. Usually we write it as, instead of divided by negative 38, we write it as negative x squared plus 6x plus 1 to the negative 19 over 38. That's more typical. Plus c.
When you anti-differentiate, like the du, like do you just like not have to deal with that?
Well, so what is the du exactly there? The du is kind of the, it's kind of the instructions of the integral. So let me actually flip the page and I'll address a little bit more. So when we write something down simply, for example, like the integral of, I don't know, x cubed dx, what this is telling us to anti-differentiate this function with respect to that variable, so that you're actually integrating with respect to the variable that we want to be integrated. So if I do this, it's going to be x to the 4th over 4 plus c. On the other hand, and this is not something we're going to run into, but just as a point, like if you had something like this, like the integral of x cubed du, well, this is now saying u is the variable, but we're trying to integrate that. So this would be totally different. So what I should really say here is that This is just part of the instructions. When you look at the integral symbol and the d whatever symbol, the variable here has to match the variables there. You can't have a different d whatever. It's called a differential, by the way. You can't have a different differential variable than your function variable. And once you have done the integration, we no longer write these symbols. It's kind of like, in fact, it's very much like writing the derivative, right? Derivative d dx of some function, like x to the 7th. This is instructions. It's instructions. They're telling us to do a thing. Here, the thing is take the derivative. So once we take the derivative, we no longer write the instructions because we've done what the instructions said to do. Same idea here. These instructions tell us to do a thing. We did the thing. We no longer write the instructions. But, and this is vital, the variable there has to match the variable there, which is why when we're doing the U-substitution, we have to make sure that the dx changes into something with du. That's really important. In fact, absolutely vital is what I should really say. Let's do a couple more indefinite examples, and then we'll start doing some definite. Oh, I think I'm looking at interesting. I think I got. Sometimes you get. Oh man. I mean, I didn't do anything wrong. I just was doing examples that I kind of. I mean, some of them are fine. Okay. Let's look at a couple more. Sure. Let's look at the integral of natural log of x over x dx. So here, there's only a reason, well, I should say, we never want to choose u equal to x. Not because it's bad necessarily, but it's not going to get us anywhere. Right? If you choose u equal to x, well then the derivative is equal to 1. So du is equal to dx. And then look what happens. So dx is du. And then replace each x with u. So natural log of x becomes natural log of u, and x becomes u. It didn't get anywhere. I didn't make any progress, right? This is still the same integral, just with different letters. And that's what choosing u equal to x is always going to result in. Is you're going to get the same integral just with u's instead of x's, which isn't helpful. So instead, we make the only other choice that seems reasonable. We let u equal the natural log of x. What's the derivative of the natural log of x?
1 over x.
Right. And we have a 1 over x. It's just kind of in this fraction. And we definitely want to write this as du equal to 1 over x times dx. And then we're going to rewrite our integral as, I'm first going to break it up so it's easier to see what I want. I'm going to write as the natural log of x times 1 over x dx. And then my 1 over x dx, that's my du. And then natural log of x, that's what I said u was equal to. So this is going to become the integral of u times du. Again, this is just instructions. We're saying anti-differentiate u. Well, the antiderivative of u is u squared over 2. And then we plug back in what u is equal to, which is the natural log of x. So natural log of x quantity squared over 2 plus c. Sure. Sorry, it's one. Okay. Sorry, I had some problems, I thought. Okay, fine. All right. Sure. Let me do one more of these, and then we'll do some definite ones. 2 more. here are a couple of examples that kind of really bring home the idea of needing to pick a u so that the derivative shows up. So if I do the integral of e to the 2x over 1 plus e to the 2x, what could I pick for u? Well, there's a few choices. The choice I'm going to make, though, is 1 plus e to the 2x. Because the derivative of e to the 2x is e to the 2x times 2. Something I want to say here. We could have just picked e to the 2x, but usually, not always, but usually, if you can tack on a constant that's added to it, it usually makes sense to you. Because picking 1 plus this isn't going to change the derivative at all. So our derivative here, du dx, is, so the derivative of e to the 2x is e to the 2x times 2. And then isolating du, or really, sorry, trying to make this side look like, well, I've got e to the 2x times dx. So I'm going to write 1/2 du equals e to the 2x dx. Okay, so I can think of this as this. So I'm going to get the integral of e to the 2x dx. That's going to become 1/2 du. And then 1 plus e to the 2x is just u. I like to bring out the 1/2, so I would probably rewrite this as 1/2 times the integral. You have a choice here, and some people like to do this different ways. Some people like to write this as du over u. Some people like to write this as 1 over u times du. They're literally the same thing, but most people find it a little bit easier to see that this one, the antiderivative, is the natural log of the absolute value of u. Whereas for some people, it can just be more challenging to see that this is the same as that. So either way you write this, the antiderivative of this is the natural log of the absolute value of u. So I end up with 1/2 the natural log of the absolute value of u plus c. And then we replace the u with what u is equal to. So I get 1/2 the natural log of the absolute value of 1 plus e to the 2x plus c. One thing to be aware of here, which is not a big deal. If you never did this, you'll be fine. A lot of the times you'll see people drop the absolute values here. The reason being that 1 plus e to the 2x is always positive. So we don't leave the absolute values there. It's also okay to leave them. And so if you're not sure if you can drop them or not, just leave them because it's always safe to leave them. Questions about this one? Okay, so now we have a very similar looking problem, but it's actually going to be very different. So now I have, instead of e to the 2x over 1 plus e to the 2x, I have e to the x over 1 plus e to the 2x. And the issue here is that if we make the same choice for u, our du is e to the 2x dx. But I don't have an e to the 2x times dx, I have an e to the x times dx. If you wanted to, it wouldn't work, but we could try to break it up. We could try to say, well, okay, 1/2 du is e to the x times e to the x dx. And then you can't really divide by e to the x here. You can't say 1/2 du divided by e to the x. I mean, you can, but the problem is if you replace e to the x dx with 1/2 du over e to the x, you're still going to have an x when you only want u's. So this one's a little tricky, and to be honest, it's one of those problems that you kind of have to see once to know how to do it. What we're going to end up picking here is, well, again, I'm going to fall back on, I want to pick u so that the derivative also shows up. Well, the only thing I really have that's not like, I should say, the only thing I have that's times dx is really e to the x. So what's the derivative that gets me e to the x? E to the x. I'm going to let u equal, not u, let u equal e to the x. So then my du over dx is going to be e to the x. So du is equal to e to the x dx. So that's great for this, right? That certainly works out there. What does that mean for the bottom? So my integral is going to be e to the x dx is just du. And I've got a 1 plus, what's e to the 2x going to be? Well, e to the 2x is e to the x times e to the x. But e to the x is u. So e to the 2x is going to be u times u, which is u squared. But look, we know how to integrate 1 over 1 plus u squared. It's the arctangent. You could write, if you don't like this du here, you can write this as 1 over 1 plus u squared du out there. That's all, it's the same thing. And then the integral of this is exactly the arctangent of u plus c, which is the arctangent of e dx. So this one I don't think is specifically very intuitive, right? It's kind of like, oh, I never would have guessed that, which is why it's important to guess like all the things, right? If you're not sure what to do and you think it's a U-substitution, just start guessing stuff if you really have no other clue. And guess simple stuff, right? You want to, it's ideally, if you're not sure, try to guess your U to be on the simpler side of things, not on the more complex side of things. That's what I would say is also a good kind of guiding principle for your choice for U. So let's look at some U-substitution problems where we have limited integration. So let's say we want to find the integral from, is that really the choice I want to make? Oh, sure, that's fine. From 0 to 4 of x over the square root of 9 plus x squared dx. And so it seems pretty reasonable here to pick u to be the stuff inside the square root that's in the denominator. Basically, if you see x to a power and then x to a 1 higher power, you're going to pick u to be the thing with the x to the 1 higher power, because the derivative of x makes the power 1 less. So if we pick u equal to 9 plus x squared, our du dx is going to be 2x. Right, so we picked u to be this, and we essentially got our derivative to be this. Right, not exactly, we're off by a factor of 2. That's okay. So then we're going to say that 1/2 du is equal to x dx. All right, so let's go on our journey of replacing things. So here's my x dx, which is going to become my 1/2 du. And then the 9 plus x squared, that's going to become u. So when we rewrite this, I'm going to write the 1/2 out in front. So it's going to be a 1/2 du. You can write the du on the top of your fraction. I prefer to write it out to the side. And then in the denominator, I have the square root of u. So if I don't write the du on the top of my fraction, I have to have a 1 there, so that the 1 times du is still the du. Now, I think Dr. Burke was very appropriate when she said, you're best off changing your limits of integration. Right? You can certainly write like u1, u2 here, and then do the integral and change it back. You don't want to do that. It is less work to change your limits of integration. Occasionally it's terrible, but almost never. So let's change our limits of integration. So here's the way I like to do it. I like to think about it as these are my x limits of integration. This is an x value, this is an x value. So all I'm going to do is I'm going to use my equation here to find the corresponding u values. If x equals 0, jam that in there, and you get u equal to 9 plus 0 squared. So when x equals 0, u equals 9. And then you have to match places, meaning since x equals 0 is in the bottom, u equals 9 has to go in the bottom. And then x equals 4, plug that in here, u is going to equal 9 plus 4 squared, which is 9 plus 16, which is 25. It's not hard to change the limits of integration if you use your choice, right? I mean, the way you have to do it, you use the thing you let u equal. I know she was showing kind of a formula where she was talking about how like the integral of f prime of g of x times g prime of x, these are like your g of a, your g of b, which is true, right? If this is my function, if I'm saying u is equal to g of x, then this is g of 0 and this is g of 4. But it doesn't have to be that complicated in our heads. We can just be like, oh, I have an equation for u. I know what the x limits of integration are. Change them into u limits of integration by plugging them into the formula for u. That's always what it is. And then we do the usual thing. We anti-differentiate this. So this is u. So this is u to the negative 1/2. I'm going to skip a step. So I'm not going to rewrite it. I'm just be like, I know it's u to the negative 1/2. I know the antiderivative is u to the positive 1/2 divided by 1/2. I still have that 1/2 out in front as well. And then I'm going to evaluate it from 9 to 25. I would probably simplify just a tiny bit first. And the nice thing here is that 1/2 divided by 1/2 or 1/2 times 2 cancels out and you just get 1. So this is literally just u to the 1/2 or the square root of u from 9 to 25, which is going to be the square root of 25 minus the square root of 9, which is 5 minus 3, which is 2. Or if you felt like making it harder for yourself, at this stage here, you could have then plugged back in that u was 9 plus x squared and then changed your limits back to x equals 0 and x equals 4. But that's just silly, right? Because if you do that, so if you did that, here's what you do. You can say, okay, I'm going to have 9 plus x squared to the 1/2 power evaluated from, instead of 9 to 25, it would be 0 to 4. You're not saving yourself any work, right? In fact, you're kind of just repeating the work you would have done anyway. Because when you plug in 0 for x here, then you get 9 plus 0 squared, which was your new u value to the 1/2. And then when you plug in 4, you get 9 plus 4 squared, which is 25, which is what your new value was right there. So it's really, either way you do it, you're kind of doing the same work of having to do the changeover. It's so much cleaner this way. So I really, really, really encourage everybody to, if you're doing a definite integral and you have to do a u substitution, I think we're all best off by changing the limits of integration. Let's see. Do I have more examples? I don't have more examples right there. Let me look over here. Oh, I wanted to say, I want to do more examples, but I also want to say stuff. Sure, let's do, yeah. One more example. And I guess we'll probably be out of time. I guess, so many things I want to say. Let's say we want to do this example, the integral from, what have we got here? That's kind of a tricky one. Sorry, I know we're almost out of time, but I wanted to give you guys a good one here. Let's do this one. Let's do the integral from 0 to 1 of the cube root of so sure 1 plus 7x dx. Okay. So we're going to let u equal the stuff inside. Our du dx is just going to be 7. So then du is equal to 7 dx. 1/7 du is equal to dx. When you're able to let u, so in fact, actually, I'll say, yeah, I have something I can't say here, which is kind of nice. So, right, things are, if the thing that's stuck inside a function is just a linear function of x, right, it's some mx plus b, the u substitution is always going to like work out relatively nicely, relatively. So this is going to become, so dx is just 1/7 du. Right? There's nothing we have to like attach onto this. We just have to say it's 1/7 du. And then the cube root of 1 plus 7x is going to be the cube root of u. From, well, it's not 0 or 1 anymore. If x equals 0, u equals 1 plus 0. And if x equals 1, u equals 1 plus 7, which is 8. And then we can write this as 1/7 times the integral of u to the 1/3 is u to the 1/3 plus 1, which is u to the 4/3, divided by 4/3 is multiplied by 3/4 from 1 to 8. So this becomes 3/28 times, plug in the 8, you get 8 to the 4/3, minus plug in the 1, you get 1 to the 4/3. It's 3/28 times 8 to the 4/3. Do the cube root first, that's 2, and then 2 to the 4th is 16. And then 1 to any power is 1. So I end up with 3/28 times 15, which is 45/28, which is a weird answer, but fine. There are so many things I want to say. So one thing I want to say, which I know I've said to a few of you a few times, is that when you integrate a function and you have a multiple of x, you usually end up dividing by that multiple of x. It's really because of this U-substitution thing and because of the chain rule, right? If we were to differentiate this, the chain rule would say we would multiply by 7. So when we anti-differentiate it, we divide by 7 to account for that. And that's exactly what's happening. That's why we're getting this 1/7 here. But really, it's also because that's how the U-substitution works. And they're all the same reason, just said different ways. So just to kind of say one more thing about this, and we'll talk more about this particular idea next Monday because it is kind of super useful. So like if you're going to integrate something like, I don't know, the cosine of 6x dx, you don't have to do a U-substitution here. You could let u equal 6x, but we know the integral here is supposed to be sine of 6x divided by 6, or times 1/6. Because, right, if you did the U-substitution, your du dx would equal 6, and then 1/6 du would equal dx. That's where that 1/6 is coming from because of the u sub.